Log on, tune in, find out. Another good idea from Cambridge.
Special predicates.
And the approximation resistance. And I decided, well, I should turn this on. And I decided to do it the other way around because I'll spend a lot of time on background. I'm not sure of the background of all of you people, but I'll start. And so first of all, I want to thank the organizers for inviting me. It's been a great pleasure to be here. Time has passed quickly though. And the other thing I really want you to do is to ask questions, okay? So, if you get a question that you wonder answered, you probably get more out of it than a usual seminar. So if you have any questions, please ask them. And so if I ever get to the linear threshold predicates, that's going to work with Mali Chirachi, Marcus Isaksson, and Ola Svensson. And I want to spend the beginning of sort of general setup. So a problem that I'll call max P. P is a predicate, it takes Boolean inputs. The number of Boolean inputs will be K. And for in the beginning, that will be like 2 or 3. And then I'll move out to bigger values of K. And these guys are Boolean inputs. And the bar on top of this negation, change this from true to false. There are M of these. And yeah. And you want to, and I'm interested in efficient algorithms. Okay, so yeah, doing board talks is always difficult, and my spelling will be off and on.
So P is any predicate.
Yeah, so I'll start with something with some simple predicate. So I'll take the predicate. So I'll be instantiating with various predicates and sort of see what happens. Okay. So let's take the simplest predicate, toolin, the XOR of 2 bits. Okay. So let's write it. Okay. You're happy with XOR? Please stop me if you're not, Don't be shy. And I'll be also interested in and I'll be interested in 3SAT. Which is taking the order of the 3 bits. Okay. And remember, I have negation. So the fact that I put 0 here doesn't really matter. I can just negate one of the variables. So this is really linear equations, mod 2, with 2 variables in each equation. Okay. And this is, 3 variables in each equation. And here I sort of go non-linear and ask for the OR of 3 bits instead. And now I'm looking at efficient computation. So let's see if we can get the audience going. Suppose I can satisfy all these constraints. The optimal solutions can in fact satisfy all the constraints. In which of these 3 cases can I actually find something that satisfies all the constraints efficiently, remember?
Maybe 2lin.
Maybe 2lin. That's a conservative statement, but correct one. Well, if I can satisfy all these equations, I can just guess one equation, the variable value for one of the variables, and I'll get it for the others, and so forth. Okay, so 2lin, yes. How about 3lin? Does anybody know how to solve linear equations? You teach it, right? Many of you. Linear equations, just, Gaussian elimination. And Gaussian elimination over the finite field of 2 elements is much easier than Gaussian elimination over an arbitrary field, because you just, you have just zeros and ones, and you don't have to invert elements or do anything bad, so it's easy.
You're talking about solving all of them? Or
yeah, suppose you can satisfy them, all of them simultaneously.
Yeah, okay.
Yeah. Yeah, good. So that's it. Yeah, I'm doing the easy things first. But if 3-sat, on the other hand, even if you can satisfy all, it's an NP-complete problem to find something, right? Well, 3-sat is NP hard. Even if I can satisfy all, it's hard to find something that satisfies. It's hard to find something that satisfies all. Okay. But this is back in the 70s. Okay. So now I want to go to optimization. Perhaps there is something that satisfies all or almost all the constraints, and I want to find something that satisfies as many as possible. Okay. So there's so few of us here, you can't ask the neighbor. You have to ask the speaker. No? Okay. So now I'll be interested in instead of questions where we want to do as well as possible. And my measure that I use for most of this talk is that you look at the number of satisfied conditions of the thing you find efficiently compared to the optimal value, which exists but is hard to find. Okay. Okay. So let's do some easy algorithm, okay? Any suggestions from the audience? Well,
Just put anything you like in.
yeah, put anything you like, and what happens then? Or anything you like, I would interpret, random. Is that? Yeah. So suppose we put something random, we don't even, worry too much about doing well. Suppose we take something random. How many conditions will we satisfy if we're working with Boolean? On average? A half, great. Okay. And so the number of satisfied conditions here will be half, and the optimal value won't be better than all. So in fact, we get a half here. Okay. What happens for 3-lin?
Also half.
Also a half, right? And 3-sat?
Also half.
Not sure I know what number 3 means.
Yeah, so that's the OR of 3 bits. One of the first should be true, the second should be true, or the third one.
7/8.
7/8. Great. Okay.
So you want it to be equal to 0, or what is the?
Sorry, yeah. So, but this is.
Oh, I see.
So it's the OR should be equal to 1, true or 1, or however we do it. This is the OR of the variables. This thing.
Oh, yeah, but then if you want it to be 1, then it should be an 8, 1/8, right?
No, the
0. 0 is 1/8 and
well, I'll confuse you. Okay, so it does. So
Oh yeah, right.
No,
You
it's
see,
okay.
sorry. No. Okay, it's my confusion. It's my
yeah, good. That's good. Yeah. Okay. Fine.
He's a nihilist.
Okay. No, it's good. It's good that you're paying attention. So let's. Where were I? Yeah. Okay. So. Okay. So the question is, what can we hope for in this world? Okay. So I don't know to what extent you know what NP complete and NP hard is, but the NP hard problems are the problems we don't think can be solved efficiently, and sort of been thinking so for 35 years or 38 years. Okay. And all of these problems, you know, maximize and finding the real optimum is NP hard. And this was known from a long time ago. Okay. And oh, okay. Okay. So getting the exact, you know, really getting the true optimum was hard. And then came the PCP theorem, which I won't explain. It's Aurora Safra and Natura Lund Mutfani, Sudan and Segeti in 92. And I won't really say what PCP is, but what we use for this, what follows from this is there is some epsilon. And this epsilon was really minute to start with, you know, 10 to the minus 6 or something. That's hard to approximate these three problems with in 1 minus epsilon. Okay. Okay. But then there were improvements, and I want to. So this is easy. And hardness. And there were a number of improvements, and I'll do some of my own result. And then I was managed to prove in 97 that this constant of 7/8 is in fact the correct constant for 3 set. Okay, you can't beat 7/8 by any arbitrary epsilon. That remains NP hard. Okay. And I got the same for 3 lin, that was a half plus epsilon, but in 2 lin you could only get the worst constant, which was 11 over 12 plus epsilon. Okay, so this is NP hardness result. Okay, and I won't really discuss this, but I want to point out that this is sort of a very nice, and I called this, or eventually was called, approximation resistance. This says that, you know, whatever you can get by you stupidly picking random bits or random values, you can't do better, you can't approximate it better in polynomial time. So this is sort of approximation resistance. Okay. So the thing that I really got interested to, and I still care very much about, is, you know, what makes a predicate hard? You know, why is it suddenly approximation resistance? Why is 3 sat and 3 lin so different from 2 lin here? And what can you say about this family of predicates?
Ah, but so you do actually know that 2 lin, you have to go higher to get NP hardness.
Well, yeah, this is where I'm turning next. Okay. So we'll get to, so what's the thing to do? Well, you can prove hardness result, which is really what I like. But of course, we have to keep an eye on the other side of things. Maybe there are smarter algorithms there. Okay, and that's, okay. So actually, I remember the 7/8 approximation algorithm appears already in the book of Gary and Johnson in the late 70s, and already then I thought, you know, this is stupid. We should be able to do something better. Just the question of proving it. And well, that turned out to be false. But now let's turn to 2 lin. Okay. So here is really a really beautiful result. let's see if I can remember this. I think this is okay. I hope I got the formula right, we'll see. So it turns out that you can approximate this within the minimum of this over all angles theta, and this turns out to be a number that's 0.878. Okay, so in fact it does answer the question, yeah, you can't get a half there, you have to get something bigger. And this is a really, so how many people saw this algorithm? Okay. So if it's really a nice algorithm, so I'll just sketch it to you. And on top of this is 1995, so it was really no surprise, you know, it was prior to the lower bounds. So what is this thing? Well, if I have an equation like this, I can write down the corresponding, and you now usually think of the y's as plus minus ones. Yeah. So if these are unequal and epsilon is 1, then in fact you get a 1 here, so you get a 1. So this exactly counts the number of satisfied equations, right? I didn't get as many nods as I want. So
there's something, the minus 1, 1 and the epsilon don't seem to match.
Well, x is in one place and y is in the other.
So these are bits, right? These are plus minus ones. So if the equation is...
Are they bits? Are they 0 ones?
These are 0 1 sort of. But the y's I want to be plus minus ones. Okay. So if 2 plus minus ones, if they're equal, then this is plus 1. And then you're sort of scoring a point if the corresponding equation is that they should be equal, you know, that the XOR is 0.
Is there a connection between the y's and the x's?
Well, the indices are the same, right? You should really think of, I'm moving from the 0, 1 domain to the minus 1, 1 domain. I didn't want you to confuse you with this, so I did.
But is yi 1 when x is 1, xi is 1, and minus 1 when xi is 0?
Yeah, for instance. Or the other way around. But because it doesn't, if you change everything, you know, you just have, if the x's are different, you have an equation with a 1, and then the y's are different, and then you get the minus 1, and things work out, okay? And this, of course, we didn't do anything here, you know, it's exactly the same problem. We want to maximize this over n things that are plus minus 1. And the great invention of Goemans and Williamson is that instead of maximizing it over bits, you want to maximize it over unit vectors in Rn. Okay. And this turns out you can actually optimize efficiently. Okay, so this is a different problem.
But that's because you use semi-definite programming.
Yeah, so this is exactly semi-definite programming, right? So one way to say this, let's write it. Why is it called semi-definite programming? So Okay. So this is exactly the same. Optimizing over vectors is exactly the same as saying that we stick a matrix here, which should be positive semi-definite, and have diagonals where entries 1. Because we know that such a matrix can be factored as V times V transpose because it's semi-definite, and then the V's are just, the rows of this matrix V are in fact my unknowns over there. Okay.
You lost epsilon.
Pardon?
You lost epsilon.
Yes, thank you. And why should this be possible? Well, it's far from obvious, but now I'm actually here optimizing a linear function over a convex set, because the set of positive semi-definite matrices with diagonal entries 1 is a convex set, and you're optimizing a linear function, so there are no local optima, so you can sort of figure out that this shouldn't be too hard. Okay. And the great idea, another great idea apart from making the program is sort of, well, this generalizes. Now I don't get back a real solution or a Boolean solution, but the way to get it back from the vector solution is you just pick a random vector. You take the inner product of this the same random vector with all the vectors you obtained, and the sign of these things will actually be a good thing for your original problem. And then you have to analyze it a bit, but this is the entire algorithm. Okay, so it's something I really like. Okay, so that was the Gell-Mann-Williamson algorithm. So let's get back. Everybody happy with this? So let's get back to the original question. Or let me do something else first, actually. Yeah. So let's see the general program. So by area, I mean approximation resistant. Yeah. So before I continue this, so this is the general program we wanted to do, but let me describe a sort of problem that we've more or less seen before, which is that let's select tool-in n, where n says that we shouldn't do it mod 2, but we should do it mod n, in fact. And in fact, let's make life very easy. Let's just look at the equation which says that the difference between two variables, for some pairs of variables, we'll sort of say that the difference should be this. Okay. Okay. And the question I want to ask is, well, here of course a random instance would give 1 over n, which is, you should think of n here as a big number. And it turns out you can always do a little better than 1 over n. That's a result from a long time ago. But the question that's been around for some time, suppose I fix a constant a very small constant epsilon, okay? And I tell you, this system is either 99% satisfiable or the best solutions satisfy only 1% of the equations. Can you determine which? Okay, so think of n as 1,000,000 or something here, and I give you this system of 1,000,000,000 equations, and I ask you, can you satisfy 99% of them, or can you only satisfy 1%? Okay. So the statement that for every epsilon, greater than 0, there is an n such that this is in fact hard. That's the unique games conjecture, if you've ever seen that. So that's an open question, is this true or is this false? Is there an efficient procedure or is there not? And this is unknown, and it's actually a very important conjecture to think about. And it's not complete, well, there's no sort of consensus whether this should be true or false. Okay? And here's actually something, if you didn't even do this before, you can actually think about it. Because suppose there is an efficient algorithm here. I mean, you have all the ingredients you want, right? Equations mod n, you sort of understand, right? And maybe you don't know too many of the algorithmic techniques around, but we know that all the existing algorithmic techniques won't be enough to solve it. So you have to invent something new anyhow. So and this is what you should do.
So you're saying anyone in this room could work on this?
Yeah.
Anyone could solve it.
Yeah. Yeah, that's a nice distinction. I like that. Okay. So this is the unique conjecture. So what's happened now is that to understand approximation resistance, it's a lot easier if you assume that this is hard, which is the unique games conjecture. That gives you a lot more information. So what I'm going to tell you, if you successfully disprove this, you've sort of ruined years of work, but you would actually bring science forward.
Can I ask you,
Yeah.
in which cases would we need to distinguish between such extreme cases?
So the question is, for any small positive constant epsilon, is it true if I make the modulus big enough that it's hard to distinguish between these cases? So if epsilon is 0.01, then you have to distinguish between 99% satisfiable and 1% satisfiable.
Yeah, the question is a little bit different. The answer really is that if this is true, it's a very powerful statement because you're asking for such a small thing to do. Right? So it's not that you necessarily want to do this particular thing, it's just that this particular thing is so little that if the statement is true, you've proved something much stronger.
Yeah, okay. So if this is hard, it's sort of a seemingly simple statement, right? So am I answering the right question now, maybe? So if it turns out to be hard, you can prove that other things are hard, right? And if it turns out to be easy, well, then it's sort of easy and that was sort of boring and it won't play such a big role in the future. But if it's hard, that's more important.
Can I have another question?
Yeah.
I wonder about this approximation resistance. So
Yeah.
assume that you have two predicates, P and Q, and you know about each of them that they are separately approximation resistant.
Yeah.
And now we consider a system of equations mixing P and Q.
Yeah.
Can you prove that then?
Not the way, I don't know I like these kind of general statements. And I don't know the answer to your question.
But you don't know.
I don't know, I don't think I know an example where it's false. I have been trying to prove general statements like this, but sometimes there's counterexamples. Okay. Okay. So let me just say something that approximation resistance is sort of monotone, okay? So this is a statement of experience. This is not really a mathematical statement, okay? And what do I mean by this? Well, suppose you have some predicate P, which is approximation resistant, and it sort of implies a different predicate Q. So this is sort of more easy to satisfy. Then usually it turns out the Q is approximation resistant, okay? And for instance, you can sort of formalize this and prove that if you take 3 lin, where 3 lin says that an odd number of things are true, right? In particular, this means that one thing is true, so it implies 3 set. And you can it sort of works to prove the statement here. Okay, but this is not true. So the only counterexample I know to this statement is that if you let P be the following predicate on 4 variables, that says that, if x1 is true, then x2 is not equal to x3. If x1 is false, then x2 is not equal to x4. This turns out to be approximation resistant by a result of Guruswamy, Levin, Sudan, and Trevisan. While this clearly implies that, well, either this is true or this is false, so x2 is different from one of these two. So not all equal x2, x3, x4 is in fact implied by this, right? And this is not approximation. But this is really the only counterexample I know to the monotonicity. So it's not really monotone, but it has some monotone feel to it. So let's take a nice theorem. So let's take a predicate and look at the strings that satisfy this predicate. That's a subset of -1, 1 to the k, right? And suppose that supports a pairwise independent measure. Are you happy with what this is? No. Let's do this. So let's take 3 lin. Well, it accepts 4 3-bit strings, right? And if you take the uniform distribution distributed on these things, each bit is equally often 1 or 0. And if you in fact you look at each pair of bits, each of the 4 values for those pair of bits appears equally often, and that's what I mean by pairwise independent. When you focus your attention on just 2 bits, it looks like you're picking something uniformly random, but in fact you're not. Okay. Let's use the abbreviation. So the powerful result of Ostrin, and I think this is 0.8 maybe. If it supports a pairwise independent measure, then in fact the predicate is approximation resistant if we assume the unique claims conjecture. Okay. And this, for instance, is nice. This sort of supports the monotonicity property, right? Because if I take a Q that accepts more things, I have more possibilities to make a pairwise independent measure. So this will remain true. So anything you prove approximation resistant by this, you can always take the monotone closure upwards. Okay. So my hope when I saw this was sort of, well, maybe we can sort of use this to get, you know, a nice characterization of approximation resistance. So let's look at the maximal things that don't satisfy this. You know, what can we say about those things? Let's use Q for it anyway. So what do I claim? Well, if you look at the maximal things, or if you look at things that don't support the pairwise independent measure, I claim that there's a very nice condition there, namely that says that this is equivalent, that there's a quadratic function, and I now think of my bits as plus minus ones. That's sort of more convenient every now and then. And that doesn't have a constant term, so that whenever p is true, then this quadratic is in fact positive. Okay. So this is sort of a nice little fact of life that I like, and you know, it might be.
And this is quadratic involving possibly linear term, or?
Yeah, it could have linear terms also. Okay, but it can't have a. So the point is that anything without a linear term has expectation 0, right? Because the expectation of each term is in fact 0. So that sort of means that this is an interesting condition. I like these little facts. You want me to, I'm sort of, will run out of time at some point, but you want me to prove this? This is sort of...
Duality or?
Yeah, it's just, you know, the convexity, you know, you have a separating hyperplane and these kind of things. So that's good. So we'll ask Keith for a proof at the end of the lecture. But this is how it works, okay? So let's keep that. So the hope I had a long time ago is that the hope was that if life is good, or you know, mathematics is simple, if you look at the maximal things that don't support pairwise independent measures are the signs of such quadratic polynomials. Because then you're sort of putting as much as you can there, and if you put more things into, you start And what we saw before is that, quadratic things are really nice for efficient computation, because there we have semi-definite programming. When quadratics are easy to understand, we can relax it, you taking quadratic terms and making them in a product. So maybe we could approximate such things. So this, I hope for a while. And there's something I never published, but I have one example of a function of this form which is indeed approximation resistant. Okay, so the generality is not true.
So can you briefly explain why your apparently plausible argument doesn't work?
No. I'll do something simpler, okay?
All right.
Okay, well, you can re-ask the questions later. If that's now, yeah, I hope to answer your question. We'll see. So, well, this sort of looks like a complicated question. I told it to my then graduate student, Austrine, which is the A in AM. He said, well, let's do this simple case first. Let's take the linears. Okay. So if there's any hope that we should be able to do the the quadratic case via semi-definite programming, it should be much simpler to do the linear case via linear programming, right? Because linear programming we do understand. Okay. So we set off to do this, and there these are, now I eventually get to the title of my talk, these are the linear threshold functions. Okay, and the question is, can we approximate these or not? And just to make things simple, let's assume that this linear function is never 0. Okay. So I'm eventually going to get to an algorithm. So I'll take the easiest of the linear things, namely majority. And why does it fit into this framework? Well, it just sum my bits, which remember now are plus minus ones, rather than 0, 1, so that things work out nicely. And take the sign, and that's the majority function. And so now we have lots of conditions of this where each is a majority. And let me even, it's not interesting for k equal to 3, but let me still do the k equal to 3 case, and then we'll see what happens for large k. But you should really think of k as 21 or 101 or something like this, so you have big conditions. Okay. So let's, so the theorem that was actually known before this, but we souped it up, is that we can do majority for any k. So if I give you a big majority, lots of conditions which are majority, we can beat the and the theorem I want to prove is that, well, what's the random threshold here? Well, majority is symmetric. If you change all the bits, you change the answer. So the random will give you probability 1/2. And I claim you can do better this by constant that only depends on the size of your majority. Okay.
You
use some algebraic stuff like finite fields for that?
No, now we're in the reals, you know, no finite fields. So let's do it like this. So let's start, in fact, with the instance we sort of sketched over here. P is now majority, so it's the sum. So I'll have the corresponding real valued thing saying that the majority of these are true. I negated x3, so we should have a minus x3. And once it's greater than 0, it's in fact at least 1, so I can write this inequality. Okay. Oh, my short-term memory is bad, so.
That's a bad sign.
What?
Bad sign.
Yeah, that's bad. So okay, so we take these and we translate them into linear inequalities, and the xi's are in -1, 1. So as a standard, when we have linear conditions, we'll just say, well, we have all these things that we want to be, Boolean value, we want them to be ±1, so just relax these so that they can in fact be, real valued in the -1, 1 range, okay? So while it's hard to find something that satisfies this with each xi to be forced to be ±1, if we relax it, we get a convex problem and we can in fact solve it and find a solution, okay? So let's see that we find some solution here that satisfies all these equations, but it's real value, so it actually has some yi is equal to some alpha i's, which are -1, 1 range. But now we want to get back to the situation where we have ±1s, and the thing is that the idea now is that we're actually going to use this real valued solution as a guidance. We're going to probabilistically pick a solution, and we use these as probabilities, which sort of makes the expectation of xi is equal to alpha. Okay. So now if you look at what we really care about is the probability that these things are satisfied. And suppose I so it's more convenient, instead of making it 0, 1, to make it ±1. So then if you look at the expectation of the majority, which is the So if I go to plus minus 1 instead of just 0, 1, so that we want to sort of to beat the expectation 0. If you just calculate the probability the majority is satisfied as a function of these three probabilities, you just see that it turns out to be a nice condition in alpha 1, alpha 2, alpha 3. And then you get also a term of degree 3 here. Okay. So then it turns out that we're almost done. Why are we almost done? Well, the alphas were a solution to this linear program, which sort of means that the sum of these were at least 1. So this is at least 1. And that sort of means that the probability of satisfying these constraints is sort of a nice function as a function of these alphas. Okay. We have this annoying extra term, but you know, in the case of 3, it's sort of easy to control, so it's not that important.
The extra term is what gives you the beats the half, yeah, isn't it? Or am I
That gives you?
Isn't it the extra term that beats the half, or am I missing something?
No, okay, so the probability, I'm making it in plus minus 1 notation. So if the expectation is, if the value is 0, then in fact you get half-half, okay? So this is sort of the linear contribution. You're sort of biasing your variables, but then you have sort of some non-linear terms. So the point is that we have control over our linear terms. That's what came from the linear program. We don't have control over our non-linear terms. But it's very easy to control the non-linear term because it's only 1 and it's fairly small in the case of k equal to 3. Okay. So what happens if we're instead thinking of, you know, let's not analyze things of size 3, let's analyze big things, you know, of size 21, and then we'll get the same nice linear term that we really know what it was, but we'll have, you know, non-linear terms of degrees 3, 5, and so forth. Okay, and we sort of seem to be in trouble. But if we sort of stick in an epsilon there, we multiply any of these guys with epsilon, which means that the higher degree terms will in fact get an epsilon cubed. Okay. So you see this, we keep the linear term, which actually we had control over from the linear program, and we're multiplying the things we can't control with powers of epsilon, and epsilon small enough, we're sort of fine. Okay. Okay.
What is this CK when k is 21? It's astronomically small?
What it looks like? Well, it's the Fourier expansion of majority, really. So we have excellent control. So
No, I'm asking about the size of this CK in your theorem.
oh, the CK. No, okay, fine. That's CK. So
what asymptotics it has? K, more or less.
So if you do it like this, you get 1 over k to the 3/2. But in fact, you can get 1 over roughly square root k if you're a little bit more clever. Okay. So it's
Not bad.
yeah.
That means you have to somehow get cancellation between the nonlinear terms for the 1 over root k, is that right?
Yeah, so for the 1 over root k, you really have to more carefully analyze. Now we're sort of feeding bias Boolean variables into a majority, and what can you say about the probability the majority is being true, and then just do very careful calculations to see that it works, and then it's, which probably exists in the literature, but we have to redo it from scratch, so we did that. Yeah, so the question is, this works for majority of any size. Does it work for any linear condition? And what did we actually use from majority? Okay. So let's see if I can convince you of something. So what did we have? We had this, you know, P is the sign of the linear form. Okay. And this linear form, you know, looked like this. And we solved the corresponding linear program. So we know that these, you know, were greater than, you know, some constant 1 or something. But when we use the rounding in the end, well, we'll use our epsilon trick. So high degree terms are you know, won't bother us. So we're really interested in what linear terms do we get. Okay. And there, in my case, I hand waved and said, well, we have the same things. Those coefficients that find the linear terms and those that actually appeared in this rounding probability were the same. But in fact, if you look at it more closely, these guys will actually be the first level Fourier coefficients of the predicate P. Okay. And for majority, these are the same, but in general, they're not.
The Fourier expansion with respect to the Walsh basis.
Yeah, yeah.
Of the sign of the, of the function, which is a sign of the linear function.
Yeah, so P is the sign of the linear function. And so let me just conclude with one example that shows that these are in fact different. So let's define republic, which is a Boolean function that we have a president and he gets his way unless he's overruled by a 2/3 majority.
Which republic are you thinking of here?
Pardon?
Which republic are you thinking of here?
Well, this is the American Senate, right? Or you were thinking about Egypt or something? Well, so this is basically right? This is that the president gets K over 3 votes and everybody else gets 1 vote. Okay. So if you look at p hat 1 and think what this actually means in combinatorial terms, this is the probability that what precedent thinks actually will work, assuming that everybody votes randomly. This is what the Fourier coefficient. So how big is this roughly, you know, in anybody wants to? So I claim this is exponentially close to 1, because if everybody votes randomly with overwhelming probability, you know, the Senate will be split roughly half-half, and the president sort of decides because he has lots of votes. Well, in fact, it sort of follows from this that the influence on the individual candidates is exponentially small, because this sort of requires that if the ith guy, there's a tie without the ith guy, which sort of means that they randomly should the rest of the Senate equal to the president. So this sort of says that even though the ratio of these weights are just a factor of k over 3, you know, it's really an exponential difference here, and the two vectors actually point in very, very different conditions. So this sort of means that the argument I sketched doesn't work. So then we spend some other time of the paper investigating, you know, what kind of weights does in fact the weights, the Fourier transform, you know, the Fourier coefficients work as weights, and it turns out that you need rather small integer weight for this to be true. And the main open question I want to end now is that we don't know the answer for the public. We don't know if it's approximation resistant or not. And we don't know of a single example of a linear threshold predicate which is approximation resistant. And that's sort of the question we started with and we couldn't solve, but we got really good constants for majority and similar functions. So let's end here. I have already a few minutes over time anyhow.
More questions?
Okay.
Thank you.